Let's start with a brief about the many worlds interpretation of quantum mechanics and, well, the problems with it. Then we will present the idea of the two worlds interpretation, based on the thought experiments and analogies introduced in this book. Here is a summary of what the many worlds interpretation says. One of the strangest features of the quantum description of reality is the idea of superposition. We cannot describe the most fundamental building blocks of our universe with defined singular properties. Instead, they seem to behave as probability clouds of all properties they might have. Mathematically, this is encapsulated in the wave function of a quantum particle or system of particles. The double-slit experiment is an illustration of why we need to describe the quantum world this way. Briefly, a stream of photons or electrons or even molecules travels from some point to a detector screen via a pair of slits. These particles arrive at the screen distributed like the interference pattern you would expect from a simple wave. Quantum mechanics successfully predicts this result by describing each particle's journey as a superposition of all possible trajectories. In other words, the particle simultaneously takes all possible paths, which means it passes through both slits. It tries out all histories between launch and landing, and those many maybe histories somehow interact with each other to determine the most likely final destination when a measurement is made. In a sense, different possible superposed histories appear to converge on one final outcome. But what causes that convergence? And in the original Copenhagen interpretation of quantum mechanics, the act of measurement was thought to collapse possibility space into a single reality, at least with respect to the measured property. It collapses the wave function. That collapse signifies the transition between the quantum and the classical realms. One of the founders of quantum mechanics, Erwin Schrödinger, criticized this, and he proposed his famous Schrödinger's cat thought experiment to highlight the absurdity. Briefly, it goes like this. A cat is in a box with a flask of poison. A machine containing a radioactive element is set to shatter the flask in the event that the radioactive element decays. If that happens, the cat dies. That radioactive decay is a purely quantum process, so it exists in a superposition of states until it is observed. It has both decayed and not decayed. But does not that mean that the entire macroscopic system attached to that quantum event is also in a superposition? If so, then the cat should be simultaneously alive and dead until we open the box. But why can't the cat collapse its own wave function? And from its point of view, is the physicist outside a quantum blur until the box is opened? And what about the entire rest of the universe that physicists or cats are not currently observing? Many adherents to Copenhagen's interpretation propose a resolution to the paradox of Schrödinger's cat. It is that quantum superposition does not extend to macroscopic scales. It disappears when different quantum scale histories diverge. This is called decoherence when the wave function describing quantum systems overlaps sufficiently. In other words, they are coherent. It is possible to get interference in the double-slit experiment and correlated entanglement measurements. But when these systems interact with their environment, coherence is lost and parallel histories fall out of alignment. They can no longer interact with each other. By Copenhagen's interpretation, we might say that the universe chooses the final outcome of all those histories. It does not exactly choose a single history. Instead, it chooses an end result, say particle location on a screen or cat alive or deadness, based on those histories. Suppose a larger number of those histories lead to a given result. In that case, it's more likely that the universe will select that outcome. Copenhagen's interpretation says that this selection happens in a fundamentally random way. It is what we would call a non-deterministic interpretation because there is no underlying predictability behind the selection. However, there is another way to interpret the transition between the quantum and classical worlds. What if the wave function never collapses? If we can imagine a cat in a superposition of states, alive and dead, why stop at the cat? What if the family of possible states extends beyond the radioactive decay, beyond the cat, and includes the observer and, well, indeed, the entire universe too? If we open the box and find that the cat is alive, it is because we are part of an entire quantum timeline in which the radioactive decay and subsequent poisoning never happened. But there is an equally valid timeline in which it did, and another version of us experiencing that. This sounds outrageous, but it is a serious interpretation of the mathematics of quantum mechanics. It was proposed by Hugh Everett in his 1957 PhD thesis entitled The Theory of the Universal Wave Function. It has come to be known as the many worlds interpretation. To outline the idea, let's talk about what this means in the context of the double-slit experiment. The Copenhagen interpretation tells us that the superposition of particle trajectories, of histories, merges into the single timeline of the observer's reality. Many worlds say this merging never happens. Those alternative histories continue, and we find ourselves in just one of those timelines. The many worlds interpretation invites the idea that reality splits into different branches every time quantum states diverge into different possibilities. For example, at every particle interaction everywhere in the universe. This would lead to an unthinkably large number of alternate timelines or worlds that contain all possible realizations of this universe since the Big Bang. The superposition of states of many worlds can be thought of as overlaid histories, slices of a universal wave function that diverge from each other as the universe evolves, but none ever vanish. Many worlds may imply that every possible version of you exists out there. You are just the one who happens to be experiencing this branch of reality. Every other possible live path, including those branching in different directions from every decision you ever made, may be just as real. The problem of the Copenhagen interpretation and similar interpretations is that you require, to give up the idea that what a macroscopic object like a detector does should be derivable of its microscopic constituents. In a sense, the Copenhagen interpretation implies that what the detector does cannot be derived from the behavior of its microscopic constituents. The problem with the quantum measurement is that now the update of the wave function is incompatible with the Schrödinger equation. The Schrödinger equation is linear, which means if you have two different states of a system, both of which are allowed according to the Schrödinger equation, then the sum of the two states is also an allowed solution. So the measurement problem is not solved by decoherence. Please watch the previous video for more details about the problems with the many worlds interpretation. The two worlds interpretation. To help understand the idea of the two worlds interpretation and how it could actually be a good candidate for a solution for the measurement problem, we will go back to the notebook thought experiment introduced earlier in this book. So, the analogy goes that we have a notebook of, let's say, 120 pages of holographic 2 dimensions films. These 120 pages would be representing our multiverses, so all the possible universes are within this notebook, including our own universe. If you look at the two-dimensional holographic page of our universe, you would not be able to tell what this thing is a hologram of unless you shine a light on it to see the three-dimensional representation of reality of this holographic film. Technically, you are outside the space-time of this holographic film, and probably you are not governed by the laws of this holographic film, including the laws of quantum mechanics. You would be shining light from outside it. The idea is that we have two worlds. The first one is in our universe, on that two-dimensional holographic film having quantum mechanical behaviors. The other one is totally outside the notebook. That is, outside our universe or multiverse and its space-time parameters. It does not follow the quantum mechanical behavior. The version of you in our universe is an observer with constituents following the quantum mechanical behavior, which requires the second version of you in the other world with constituents that do not have quantum mechanical behavior. Even if the idea of the multiverse is eventually proven correct according to the proposed two worlds interpretation, the multiverse will not necessarily imply that there are many versions of you doing all possible scenarios. The two worlds interpretation suggests that there is only one version of you acting as an observer with constituents that do not have quantum mechanical behavior. The second version is acting as an observer of the first version. But the second version does not require an observer because its constituents do not have quantum mechanical behavior. Many questions, yeah? The great thing about science and thought experiments is that when you figure out one conclusion or follow a line of thought that you think will lead you to explain everything, it almost instantly opens doors for further research, keeping us busy and thinking about the quest to get closer to the truth. And as I always say, science is the crawling of humanity towards the truth. Yet when we discuss an idea like that, we need something testable, reproducible, and if possible, observable. We know that the many-world interpretation is not yet observable. Yet the mathematics of quantum mechanics suggests the idea of the many worlds interpretation. The idea of the two worlds interpretation could potentially be a candidate to solve the measurement problem, which could potentially be mathematically verified. Additionally, the idea of the imaginary complex forces, their properties and operations introduced in this book could provide a good basis for developing more sophisticated mathematics for the two worlds interpretation. The two worlds interpretation also implies that when an act of measurement happens by the first version, which has quantum mechanical behavior, a simultaneous act of measurement is required by the second version in the other world that does not have quantum mechanical behavior. So let's get back to some of the questions that might come up about the two worlds interpretation. For example, where exactly is that second world or version if it's supposed to be outside the multiverse space-time? What kind of laws does it follow, especially if it doesn't have quantum mechanical behaviors? And how does it interact with our world? Does the second version actually impact the first version? And if so, how? Could the first version impact the second version, its observer version? And again, how would that work? Why is an HD entanglement operation required with our observer version? What would be the source of knowledge or information for your other version in the second world? Why do we need this whole loop of encoding information between the two worlds in the first place? What happens to all the other possible scenarios? And what exactly would the second version be doing? Well, of course, not all the answers are available just yet, and honestly, there could be even more questions. Still, at the very least, we can try to approach solutions for some of these questions. So, where is that second world or version if it's outside the multiverse spacetime? The potential answer might be based on the straight line analogy introduced in this book, where we have three different representations or reconstructions of reality, in one dimension as a straight line, in two dimensions as a holographic film, and in three dimensions or even four space-time dimensions. The information is actually coded and scrambled into the two-dimensional holographic film, and additionally, it's also coded and scrambled into the one-dimensional straight line. The thinking goes that the other world is even outside the space-time parameter of the straight line. Space and time are defined differently in that world. They could potentially have a totally different meaning. They could be meaningless as well in an attempt to visualize it, which brings us to the next question. What laws does it follow if it does not have quantum mechanical behaviors? The potential answer to this question could be based on the imaginary complex forces, their properties and operations introduced in this book, which might not give the full answer, but at least something to begin with. The three imaginary complex forces are the higher dimension force, or the HD force, the balancing force, also known as the B force, and the retrieving force, or the R force. The main operations of these forces are the higher dimension force, or HD force, involves scaling, projection, entanglement, and paradigm shifting. The balancing force, or B force, is all about resonance, and the retrieving force, or R force, deals with creation and annihilation. It is important to emphasize that the entanglement operation of the HD force does not necessarily behave as a quantum entanglement. This brings us to the next question. How does it interact with our world? Does the second version impact the first version? And how? It is essential to highlight that your observer version in the other world is a version of you that does not deterministically tell you what to do or sort of control and order you what to do or what not to do, nor does it control your fate or decisions. But without getting too philosophical, it would be merely an observer with constituents that do not follow quantum mechanical behavior, yet it might have some sort of impact on you. The potential answer to this question could be based as well on the properties and operations of the imaginary complex forces, like scaling and projection, entanglement, resonance, creation, and annihilation. It is essential to highlight that this will mostly not fully follow the quantum mechanical behavior. Yet the mathematics of quantum mechanics could provide a basis for understanding these sorts of interactions. The introduction of the in sign to the Schrödinger equation, as explained in the books The Big Defreeze of the Universe and Quantizing Emotions. The basic mathematics of psychology could also be a good basis for understanding this interaction. So, the three imaginary complex forces could actually be unified and help in these kinds of interactions between the two worlds, which will be explained in further detail in the next section of this book. The mechanism of the entanglement between these two worlds does not necessarily follow a quantum entanglement behavior. Please check the mechanism of the entanglement of the HD force introduced earlier in this book. Briefly, the nature of the entanglement properties of the higher dimension force, or the HD force, is not necessarily always as quantum entanglement. Potentially, for the mechanism of HD forces entanglement, the HD forces entanglement will not be limited to a specific number of states. Partial entanglement could be allowed, which means that the two entangled systems could be partially entangled, in a sense that some of the properties of one of the systems or fields could be entangled with some of the properties of the other system or field, and not necessarily the entire system or particle. Fading of entanglement could be allowed and tracked as well. The term fading of entanglement would probably be more accurate than using decay of entanglement. The HD force could choose to pass the information to an imaginary particle or field, which is not limited by our space-time parameters. Then this particle or field would be entangled with the particle or field defined by our space-time parameters. Could the first version impact the second version, its observer version, and how? This would be a bit tougher question to answer, yet the potential answer could be in the topological manifolds and manifold bundles mentioned earlier in this book, specifically the C-line bundle. If we consider a map sigma that starts in the base manifold M and maps into the total space, so sigma goes from M to E, it's not in the projection direction, it's actually the other direction. Such a map is called a section of the bundle. If you can apply the map sigma to go from M up to the total space, and then you apply the projection pi afterward, and if this leads you back to the identity on the base space, IDM, then you have a section. So pi composed with sigma equals IDM. Yet here, if we consider the straight line as the total space and our world or universe is the base space, we still have an issue. Our observer version is outside the space-time parameter of the straight line or the total space. So how would the first version impact it? And the potential answer to this would be in the HD force entanglement mechanism, which is not necessarily quantum entanglement. The thinking goes that when an action sigma is mapped from our base space, in other words, our world or universe, to the total space, the straight line, and coded in that straight line, an HD entanglement operation could happen with our observer version. Stay tuned. In the coming video, we will try to answer the rest of the questions asked in this video.